In this lecture, we're going to be discussing proportion and scale. The lecture material is taken from Chapter 6 in Form, Space, and Order by Francis Chang. And we're going to be talking about different elements of scale and proportion, and also comparing them to some examples of architecture in the book, and also discussing the architectural theory behind some of these ideas. Now, when we're talking about proportion and scale, they're definitely related ideas. So typically when we're talking about scale in architecture, we're talking about the size of something as it relates to something else. So something else might be a human. So when we're talking about human scale, in this photo we can see that there's this large building, but until we start looking at individual items that give us a sense of how big it is, we are trying to adjust to its scale. So the scale of the humans on the street, the very tiny glimpse that we get at the bottom of the photo of some cars, some street signs, some people kind of in the foreground and in the background, that gives us a sense of the scale of the building, meaning the size of it in relation to other reference objects. Now, those reference objects could be human beings, but they could also be other buildings. They could be other things that in our mind we know how large those things are, so we can kind of compare and contrast those with the building that we're looking at. Usually when we're talking about proportion, we're talking about the relationship of parts of the building to each other. So we might look at, one part in relation to the overall whole, meaning does this kind of fit in relation to what else is going on in the building? Is it harmonious, meaning do the parts work together, like do the different sizes of the pieces complement each other, or are they kind of in conflict with each other? If we were looking at the proportion of the parts of this particular building, we would probably look at the opening sizes in relation to the kind of pilasters or projected columns that are shown. We would look at the cornice, kind of the top of it going around, and the balustrade that sits atop the building and at the base of each of these upper level openings. So we would start to look at the measurement of these pieces and think, do those look like they are properly relating to each other, or what we would like to do with the design of these in order to make them more harmonious or proper, or maybe we want them to be incongruous, but those are things that we look at with proportion. So proportion is really looking at the relation of the parts of the building to each other, or to the overall composition of a facade or elevation, or the overall design of the building. When we talk about proportionality or proportions, one type of issue that we start to look at are material proportions. So when we talk about material proportions, we have to look at where the material is coming from. We use man-made materials, we use natural materials in the course of constructing buildings, and so if we take one example, which would be wood, then wood comes from trees, so it's a natural material, and because of that, there are certain proportions that wood can or cannot have. So first of all, the size of it, we're looking at a maximum size based on the size of that tree. So the tree is going to be cut up, and if we want a straight piece of wood taken from that tree, then we've got to get probably right at the heart of the trunk, and you're only going to be able to extract a certain amount of material, and it's going to have certain proportions. So when we look at individual materials, each material has its own properties, meaning it's got certain levels of hardness, strength, durability, resistance to the elements, and certainly when we talk about strength, that's really closely related to material proportions. So if I have a piece of wood that is really long, and it's taken from this one tree, and it's a single cut, so I haven't like glued it or attached it to other pieces of wood or other materials, then that piece of wood can only span a certain length without increasing in its width and depth and thickness. So if I have, for example, a 2x4, then that 2x4 is only going to be able to span a certain distance lengthwise before it starts to either sag in the middle or before it starts to fail or starts to break or crack or show some signs of weakness. And so then if that's the case and we still have a need for using that particular material in a particular application, then we would need to increase its material dimensions, or its proportions would need to increase. Meaning, like, once you increase the length of it, then the width and thickness and depth of that material need to increase also. So proportionality applies not just to a whole building, but it applies to various parts of the building. So when we're talking about proportions, it's how the parts relate to one another. So it's almost like when one increases, then the others need to increase in order for it to function properly. And the same thing goes for other materials that are man-made. If I have a brick, typically the brick is going to be longer in one dimension, kind of the elevational dimension that we typically see at the side of a building. And if that length were to increase, then likely the depth and height are going to increase as well. Now, sometimes when you have something like a brick, it has certain modular proportions, meaning they're more standardized. But wood has that too, so you'd have like 2x4s and 2x6s and things like that. But when we're looking at those materials as a whole system, you want to make sure that you're keeping with the proportions that are either standardized or that will be applicable to the most suitable application of that material or the most suitable use of that material. Now, sometimes we have material proportions, and depending on the properties of the material, just because you increase one dimension and increase the others in relation to that, that doesn't mean it's always going to be structurally sound or structurally viable. So, for example, in the case of that wood beam, if I increase the length of it, I probably need to increase the depth and width and thickness. And at some point, you're going to reach a point where you're not going to be able to cut a beam that's big enough out of this single tree in order to get the proper length. So then you might need to make an engineered beam where you kind of take different parts of wood and glue it together in a different way. But if you had something like a stone slab, like let's say we had a slab of granite that we were going to put in a countertop application, and usually that's somewhere between like an inch or 3 inches, maybe it's like an inch and a half or 2 inches. So let's say the slab is 2 inches thick and it's 4 feet wide by 8 feet long. So at some point you're going to increase the size to the point where you're going to need intermediate supports. So maybe you can get about 3 or 4 feet wide and have it unsupported in the middle, But if you keep increasing that size and you say, well, okay, now I want it to be 8 feet between the supports, then that material, based on its thickness and its material properties, would probably just crack or collapse under its own weight. So it would need to be supported at intermediate points along its length. The same thing goes for its overall proportions. If you said, okay, I want to make this, this slab 50 feet long, and you just say, well, if I want to make it 50 feet long, I'm just going to increase its thickness by that same amount. So, it's not really practical to say I'm going to have this granite slab that's 50 feet long and a foot deep or a foot thick, because then its own weight is so great that it really can't be supported in a practical way, and then it starts to crack and break and collapse under its own weight. So you really want to look at the properties of the material and then alter its proportions, or try and make the best application with the proportions that will be most correct for its structural needs and the cost benefit of using that material, and also the best performance and functionality of that material. When we talk about structural proportions, we're talking about both visually and structurally how one material supports another. So this is Stonehenge in England, and this is kind of almost a cartoonish example of structural diagramming in terms of having a post and lintel system. So a post and lintel, or a post and beam system, is where the posts are the vertical elements and the beam or the lintel is the horizontal element. And you can see how, in a very simple way, these stones, just based on how they're propped up and their location and their size, are able to support one another. So there isn't anything else going on except just these stones being supported. So when we look at the post stones, or the vertical pieces, they're very wide. In fact, one of the ones kind of toward the right of center is tapered so that it is a little bit smaller at the top and increases in width down toward the bottom. And that is a structurally beneficial shape because the amount of weight that it needs to support actually increases as it gets further away from that post object, or further away from the lintel, and needs to be supported toward the ground. So this is almost a diagrammatic way of showing that this is structurally supportive. Now, it's also visually supportive in that you've got these really heavy, chunky pieces of stone supporting these other heavy pieces of stone turned on their side. Now, could you have a smaller piece of stone supporting those beams or lintels going across? Yes, probably, but based on the technology that was probably available and the stones that were available, we think that this is a really acceptable and adequate use of this post and beam technology, and obviously it's held up for thousands of years. So the other thing that it shows is you've got these supportive pieces, and then the pieces that are resting on top that are being supported end right in the middle of those posts. So you have enough of the support on either side where they're not going to fall off, it's not going to break down the support piece, and they're going to be equally supported at the vertical side, and then those horizontal pieces have enough material that's supported on their ends. So the structural proportions of this are both structurally useful and visually useful. So it allows all the loads to be transmitted horizontally across the part that's open, and then there's enough support there by the vertical posts that those loads can be transferred down. And when we talk about structural loads, it's just the weight or the actual heaviness of the object that needs to be supported. When we talk about manufactured proportions, we're talking about objects that have been created in a factory condition, and they could be all kinds of materials that are used in architectural applications. So it could be something like concrete masonry units, like we're looking at here. This is looking at an elevation view of a concrete masonry unit wall or CMU wall. And those blocks each have definite standardized manufactured proportions, meaning for its overall length, it has a certain height, has a certain width and thickness, and the proportions of those are a 1:2 proportion, meaning the height of this is half of the width. So what we're seeing there on that side is 2 times the height is the width. And so you have this 1:2 ratio that you see throughout this system. And you have manufactured proportions in all different kinds of materials. So you might have some series of windows and doors that are going to be in an architectural project, and those are going to have definite dimensions from the manufacturer, because the manufacturer makes a certain amount of windows and they have a certain amount of sizes. They probably have standard sizes, and they have catalogs that they put out of their standard sizes. And so those manufactured proportions become really critical, not just for the person selecting it, either the architectural consultant or the designer, but also for the manufacturing, that they have systems in place that have determined those proportions, and those are the most beneficial in terms of that material working properly. Now, there are several proportioning systems that we're going to be discussing, and some of those proportioning systems have been around for a very long time. This is a sketch or a drawing done by Leonardo da Vinci, and this is the Vitruvian Man. So the Vitruvian Man might sound familiar. So we talked about Vitruvius, the architect. Da Vinci drew the Vitruvian Man based on those principles that Vitruvius laid out for things that were harmonious and visually appealing and functionally appealing. And so Vitruvius talked about firmness, commodity, and delight. So the Vitruvian Man says, there are certain proportions that relate to a human being that are going to be delightful and proportional when that is applied to architecture. So if you have something that is way out of human scale or much closer to human scale, that the Vitruvian Man kind of dictates that the things that are closer to human proportions or human scale are going to be more harmonious in terms of their proportion relating to architecture. Now, there's a lot of debate about whether this is, the ideal, but there are a lot of proportioning systems that we can utilize to kind of check designs as we're creating them, or if there's an existing building, we can analyze their proportioning systems to try and learn more about the rules or systems that they use to design it. Now, one of the first ones that we talk about is the golden section. And the golden section is an ordering system that can be applied to classical architecture. When we talk about classical architecture, a lot of times we're referring to ancient Greek or ancient Roman architecture, but it can also be applied to a variety of buildings. And what it says is that you have parts of the building, and again, we're talking about proportion, so we're talking about how different parts of the building relate to the other parts. And it says as you start to draw different proportional sizes onto the building, or you start to apply these kind of sectional areas, that they relate to each other in a way that they create ratios. So if I look at, the one side of this golden section, this one kind of creates a swoop, so you can kind of create this curlicue, almost looks like a nautilus shell. But basically what you're doing is you're breaking it down into larger and smaller rectangles and then measuring those and seeing if those are proportional. Like, is it 1 to 2, or is it 3 to 8, or whatever the ratio happens to be. You can start to measure and see if those different parts relate to one another. Now, in the book, it kind of raises a good point. Like, do we even know, or can we even tell that something is designed according to some of these proportioning systems? And the answer is yes, on a subconscious level, probably. You probably aren't going into a building and saying, this is exactly in keeping with all of the tenets of the golden section. But you might go into a building and it feels right to you. It feels like it is working together, like the individual parts are in keeping with each other. There aren't things either visually or spatially that you're sensing that seem out of proportion or out of scale. But a lot of times that's because the creators or designers of the building worked very hard to make sure that the different parts were proportionally related to one another. So the golden section is one that can often be employed. It's a system that can be employed to kind of double check the parts of your building and make sure that they are relating to each other in a rational and geometric way. So sometimes we look at this in a mathematical way, sometimes we look at this visually, but the golden section is something that can be actually physically measured mathematically. The golden section is also referred to as the golden mean or the golden ratio. And this word mean, M-E-A-N, you sometimes hear when we're talking about architectural ordering systems or proportioning systems. And literally the word mean tends to be the midpoint between 2 points or 2 objects. But here I think we're talking more about that harmonious balance between spatially hitting something that is desirable or proportionally desirable. So the golden mean describes this curvature that kind of looks like a nautilus shell here, but all that's happening with this curving line is that it's forming a continuous line through these rectangular and square areas. Now the other thing that's happening is that when we have something like the golden section as the ordering system, we can find out exactly what the mathematics are of our proportioning system. That's why it's often referred to as the golden ratio. So where does this ratio come from, and how do we figure this out mathematically? So really the golden section and golden ratio is derived from Fibonacci numbers. And the Fibonacci numbers were created or kind of tapped into by a man named Fibonacci. His name was Leonardo Bonacci. Some people call him Leonardo of Pisa. He was born in the 12th century, and he was an Italian mathematician. And he's kind of the father of modern mathematics. And when we look at the Fibonacci numbers, the definition of them is adding together integers or sequential numbers and hitting on certain numbers in a series. So the way the series works is you start with 0. 0 plus 1 is 1. And then you add 1 plus 1. And then you add 1 plus 2, because those are those two integers. And then you add 2 plus 3. 3 plus 5 is 8. And then 5 plus 8 is 13. 8 plus 13 is 21. And you kind of see how this sequence goes along. And when you look at the bottom row, when we're looking at the actual Fibonacci numbers, it's 0, 1, 1, 2, 3, 5, 8, 13, 21. And a lot of those are referenced in patterns or ordering systems in natural objects, in things like flowers, petals, pine cones, leaves, even pineapple skins, and all other kinds of things. But the way that the golden section is derived is by taking these numbers and creating actual areas out of them. So when we look at the figure on the right, if your area is 21, or you've got a ratio that it has some number on one side or some number on the other side, and if this is a square, then you have the square of 21. It is equal to both sides of that square. And then you have a smaller square where the area is 13 that's proportional. Then that adds up to all of the areas of the smaller squares put together. And the same is true if you look at the figure on the left. It's still holding the same proportional relationship, even though the numbers are different. And so that's kind of the magic of the Fibonacci numbers, is that they're proportional and rational in that those ratios all relate. And so you can kind of keep increasing the actual number value, but those sizes will still be relating to each other in the same way, and they will still be proportional. So often we refer back to these numbers when we're looking at things like the golden ratio or the golden section. There are other ordering systems that rely on the logic of the Fibonacci numbers, such as the modular, Le Corbusier's ordering system. And often when we're looking to see what will be pleasing and proportional to the eye, it's a little bit deceptive, because everyone's perception is different. Everyone's perception of space is different. Sometimes when we are in a rectangular room, it can actually seem square depending on the width or depth or height of the room. And if we're in a rectangular space, it can often seem longer than it actually is, or shorter than it actually is, depending on our point of view or our perspective within the building. So sometimes we go back to these more rational ordering systems so that we can kind of control the perception of that space a bit better and make sure that the parts are relating to each other in a way that is mathematically desirable, I suppose, or theoretically desirable, in that they relate to each other and they are forming another whole that is also, relating as a ratio back to those original smaller areas. When we talk about proportioning systems like the golden section, and there are several like this that we'll look at, but one of the ideas of the golden section is that you can draw these lines, which we refer to as regulating lines. You can kind of draw them either on the elevation or the plan of a building, and you can start to see shapes and sizes that relate to one another. So this image that's shown is of Notre Dame Cathedral in Paris, and when we're looking at this, you might see some architectural ideas like symmetry and proportionality and balance, some of the things that we talked about earlier in the semester. But here you can physically start to measure, like, oh, okay, if I break down top to bottom the different pieces or parts of this, then these are equally spaced chunks of the building. So that lower kind of entrance tier of the building is 1/3 of the overall height, and then the middle part is another third, so equally spaced, and then the towers are also 1/3. And if you start analyzing it mathematically, it makes more sense that visually it would seem like it's balanced and had proper architectural proportions. Now, if you look at the width of this, or kind of the side-to-side elevational relationship of the parts, then that also is 1/3 of those individual pieces. Now, that doesn't mean that the 1/3 at the top is the same distance as the 1/3 on the side. It just means that in relation to those other vertical parts, those are equally spaced going side to side or left to right. And then on the right, we can start to draw more complex regulating lines. It's basically saying the same thing. We've got these, third or equally spaced proportions. We can start to draw these diamonds or kind of zigzag lines that all start to relate to one another, and you can start, even within those thirds, as you go up, you can start breaking down the individual pieces, like how tall are the archways, how tall are the doorways, how tall are the openings. Do those relate to other pieces of the building? Are they proportional, with the other entrances or with other parts of other side elevations? But those regulating lines are the actual lines that you start to draw on top of the drawings of the building, or even photographs of the building, to start to make sense of its parts and its individual sizings. One thing that we talk about when we're discussing classical architecture are the classical orders. And there are 5 main classical orders. A lot of times, we'll be discussing Greek and Roman architecture when we talk about the classical orders. But the 5 main ones that you want to remember are the Tuscan order, which is shown on the right. This is the most simplified of all the orders. And then the Doric order. A lot of times people can remember this best by the type of columns that are utilized in each of the orders. So the Tuscan column is fairly simplified at the top and the bottom, but it does have a base at the bottom. The Doric column is the only one that does not have a base, but is typically a fluted column, meaning it has some ridges or ribs that go all the way around the side or the length of the column. And then the other columns are fluted, the Ionic, Corinthian, and composite column, meaning it has the fluted base, or kind of the ridged base, or the ridged column, but it does have a base at the bottom. So when we look at Ionic, its trademark is kind of the curly cues at the top, and Corinthian has the leaves, these acanthus leaves, and the composite column has both. So when we talk about something that's composite, it's typically 2 materials together or 2 parts together, and the composite column combines the capital or the top of the column at the Ionic order and the Corinthian order. So oftentimes you're going to be looking at the type of column that's used to determine the order. Sometimes you'll look at the frieze or the entablature, which is the top piece of the building that is being supported, that looks like a bunch of crown molding, but those have different features and different parts that would be associated with each of those orders. The Doric order has kind of a patterned entablature, patterned frieze that has these individual features that relate to one another. And then Ionic, Corinthian, and Composite are very closely related, but you can see that Composite really combines all of the features of both Ionic and Corinthian. There are several Renaissance theories related to architecture and proportioning that were employed by various architects during the time of the Renaissance and specifically the Italian Renaissance. One architect, Alberti, designed a church called Santa Maria Novella, and he utilized different ratios that were related to the Greek musical system that were originally kind of derived by Pythagoras of the Pythagorean theorem. And so there are different methods that people would use, especially during the Italian Renaissance, to have something that was perceived and appeared to be harmonious, but also felt balanced and desirable in a way that maybe hadn't been specifically defined before. And so, when we talk about people's perceptions of space being different and people's visual perceptions of what is pleasing as being different, then if you're trying to make a common thread between being visually and spatially appealing, then a lot of architects during the Renaissance would start to mathematically try and hit these certain targets so that they were kind of sure that over and over they had something that spatially felt right and visually appeared and felt right to them. Now, one architect who employed these specific traditions or these specific types of proportioning systems was Andrea Palladio. And in that previous slide that we saw, that was the Palladian Villa Rotunda. And he was influential for a variety of reasons, but in his book, The Four Books on Architecture, he followed in the footsteps of Alberti, which was one of his architectural predecessors, and he proposed these ideas for the most beautiful and proportionable manners of rooms. That was kind of his idea. And so he had a theory that the heights of rooms could be determined by the width and length of the room, and so that there was a proportional equivalent that would feel spatially correct when a person was in the room. So he had kind of three different methods of determining that. So if we break it down mathematically, there's the arithmetic mean, the geometric mean, and the harmonic mean. Now, what that says is in the first kind of theory, that rooms with flat ceilings should be equal to their width, the height of rooms of flat ceilings. So if you had a room that was a certain length and a certain width and it had a flat ceiling, then that meant that you should have a height that was equal to the width. So that's saying, that's kind of that arithmetic version where it's like if C is kind of the wild card component that's not the length, then the width and height should be equal to one another. Now, if you had a square room that had a vaulted ceiling, then the height of that room should be 1/3 greater than the width. And this is all Palladio, using his theorems. So that's kind of the geometric approach where you have the height that's 1/3 greater than the width, and so that would give you a greater sense of space above you, and because the sides were proportionally square, then you would have enough height kind of above you to make it feel like the room wasn't kind of crushing down on you. And then in the harmonic mean, it talks about utilizing Pythagorean theorem and Pythagoras' theory of means to determine their heights based on the extremes of the width and length of the room. So that was a bit more variable, but that depending on any type of room size, you could mathematically determine the ideal proportion for the height of the room. And so it really introduces the idea of spatial integrity and spatial beauty in a way that doesn't just address the plan, it doesn't just address the elevation, it takes the whole spatial experience of being inside of a piece of architecture and trying to really target what is most beautiful and what is most pleasing and beneficial in terms of experiencing that space or experiencing that building. The modular is another proportioning system that is based on several of the things that we've talked about. It's based on Fibonacci numbers, it's based on the golden ratio, the golden section. And this was created by the French architect Le Corbusier in the earlier part of the 20th century. And it's kind of taking a lot of those previous theories of proportionality and incorporating them into not only the architecture, but relating them to parts of the human body. So this sketch, and this is quite a famous drawing in architecture. Sometimes people refer to this as modular man. So the modular is this system, but modular man is, hitting these individual parts of the human body and saying, okay, there are these proportions from, the bottom of your feet to your waist, and then up to the top of your head, and then, from your elbow to the top of your fingertips if your arm were raised. Now, obviously, this is not universal, and it's not universally applicable because people have all different dimensions and shapes and sizes, yet relating it back to the scale of human beings at least gets a target for what is going to be more in keeping with human beings and human scale. If you are designing to the modular, you can have a building that's actually quite large and a really complex facility, but if the spaces within it are relating back to human sizing, then you can have many people occupying a very large space and still make it feel like you're not overwhelmed by the building, and it's still designed for you as a human. Now, Le Corbusier kind of tried out this theory in several of his buildings, but one that he is particularly known for is the Unité de Habitation in France, and it's because it was a fairly large kind of apartment buildings, but it was a housing complex. And so if you took the housing complex and just looked at it as a whole kind of chunk, it's actually quite a large facility that could be very overwhelming if you looked at it in terms of a human. But the interior spaces, because they related back to human scale, the experience of going through those different spaces, it doesn't seem overwhelming, and in fact can house many people comfortably instead of making the building seem like it's the kind of brutal, large object that's kind of swallowing people up. So relating to the human body proportions and also the functional dimensions of a human, like where your knees are, where you might bend at the waist, where you're, comfortably sitting. And he had some other sketches where he showed, someone sitting at different, heights depending on their task, like if you're sitting close to the floor and perhaps reading, or if you were sitting and eating, or standing with your arms folded, or, standing reaching up. So Modular Man is standing and reaching up because that's kind of the extent of what would be comfortable or what would be necessary in terms of spaces relating to humans. So once you get past where people are able to reach, then you're kind of out of the zone of what is functional and proportional for people in using a particular space. The other thing that Le Corbusier did to apply this theory to his architecture, and again, at the Unité d'Habitation in Marseille, he used the strategy of placing windows and placing openings where they would be related to people performing different functions within the building. So instead of just looking at a building as an isolated object and kind of looking at it from the outside and saying, okay, here's the elevation of the building, I'm going to put a bunch of windows like this because I like the way they look as a building, he really, placed people inside of this building, and there are little openings kind of all over, and if you look at his drawings, it shows people, sitting and reclining, and then you can look out and have a view from that place where you're sitting, or you could be walking upstairs and looking out. You can be kind of standing and walking past and then have a window at head height. So all of these things kind of relate back to you as a human so that you're experiencing the building in all your various activities, and it doesn't seem like the placement of windows or the placement of openings is arbitrary and more related to the building, but it's more related back to the occupants or the inhabitants inside of it. The next ordering system that we look at comes from Japan, and it's based on a traditional Japanese measurement unit, and that measurement unit is the Shaku, and originally it was actually imported from China, and it's very close to the English foot, and it's divisible by decimal units. But if we kind of look at this in terms of how many shaku the individual unit is, then that's typically how people measure this. So there are kind of two different methods that we look at when we refer to the ken. And the ken is it's not just a measurement for the construction of buildings, but it's also an aesthetic or visual module that orders how Japanese architecture is structured, how it functions, and where partitions are placed or where openings are placed. And so it's a very rational system based on the number of these individual units that can be placed in there. Okay, so there are kind of two different ways of looking at this. So the ken, you can look at it as a modular grid system, and it's developed in a couple of different ways. And so the first way that we look at it, it's the inakema method or the tatami method. There's a standard tatami floor mat. So when we're looking at these individual rectangles that go together, that's a standard tatami floor mat. And the proportion of this is basically 1:2. So it's a 1:2 module, meaning the width is half the length, or the length is twice the width. So depending on, however you measure it, it's roughly 3 feet by 6 feet, give or take, but it's 3 by 6 shaku. So that's the measuring unit. And so in the first method, the floor mat varies slightly when you have interruptions or columns or other things that are placed within the building. So you might alter the mat to kind of move around that column, or you might move around that particular partition, and you might even vary it slightly to accommodate the thickness of something that it's touching. The tatami method, while it has these mats, is slightly more variable. And then the Kyoma method is much more constant, so it's quite a bit more measurable and a bit more rigid, because the floor mat size in the Kyoma method remains constant, and it's a 3.15 by 6.3 shaku dimension. And then instead of changing the floor mat to accommodate the column spacing, their column sizing, the column spacing changes to accommodate the size of the room and the shaku. So the size of the room is designated by the number of floor mats. So the floor mats really dictate kind of everything that's going on in the room. Now they can be arranged in many different ways, and so sometimes a room is described by how many mats can be placed in the room. So there's a 3-mat room, if we look at it kind of on the left. The next one is a 4.5 mat room, so you have kind of this pinwheel effect. Then there's a 6-mat room, an 8-mat room, a 12-mat room, and these just kind of keep adding on to each other. And you can see that the proportions of these start to kind of go back and forth. So there's like this proportional rectangle, and then a square, and then a rectangle, and then a square, and then a rectangle, and then as you keep adding, depending on what side you add them to, you're going to come up with a square or kind of a proportional rectangle. So it's a really interesting system, and we look at traditional Japanese architecture to show either one of these methods, either the tatami, the mat method that kind of varies to accommodate the columns or partitions. Typically it was an open space, so there's usually a room with columns, or the Kyoma method where you have the mats really driving how the space is designed and how the room designs, it operates, and how it functions. Anthropometry is the study of the human body, and it refers to the measurement of the size and proportions of the human body. So when we're talking about using anthropometry as a design tool, we are really using the human body to drive a lot of the design choices within a space or within a building. And we're looking at things like, how do people function within a space? Where do they sit? Where do they stand? How do they stand? Where are they looking? What is their visual perception? How much can they rotate their head? What's their peripheral vision? I mean, it really gets into how people perceive space and how they utilize space. Now, there's also another field of study that is developed based on anthropometry, and that's ergonomics. So that's kind of the applied science that coordinates the design of environments and architecture and systems that really are in concert with our psychological functions, our physiological and physical functions. Anthropometry often looks at different people and different groups of people and how they utilize space. Sometimes we look at persons with disabilities and how they are able to access specific spaces, how we can design things so that they are most accessible to most people, and we're not limiting who can use a space based on your physical ability. And so anthropometry is critical in terms of commercial construction and just modern construction that allows for the greatest number of humans to be able to use any particular space. Now, when we're talking about residential spaces, you might be looking at something that is much more customized and much more in tune or designed to a specific individual. And in that case, the anthropometry measurements can be much more specific. Sometimes, in commercial construction or buildings that are designed for a large number of people, we're trying to look at averages, average sizes of people, the ability of most people, regardless of ability or disability, to be able to use a space. But in the design of a very specific private space, like a residential space, you can get into a person's actual sizing, actual ability, and it becomes much more customized. But it's really the general study of the human body and what you're able to do physically and how you also perceive things psychologically. So not just where things are placed, although it involves that, but it can also involve things like color, how we perceive texture, the tactile nature of buildings, how we're able to move throughout the space, where lights are placed and appliances and fixtures and walking surfaces and all kinds of things. So it's a really kind of extensive system for proportioning, meaning you're just measuring everything and how far someone can reach to open a door, or how much they can turn their arm or turn their hand in order to open a door. So it's something that is really extensive, but also really helpful to the designer to be able to reference all of this information and data and incorporate it into the building so that it is as functional and beneficial as possible to the greatest number of people. When we talk about scale, typically we're talking about a building or something in relation to something else outside of it. So when we're talking about proportions, we're talking about how the building relates to itself or how the parts of the building relate to each other. But with scale, we're talking about how it relates to an unrelated or reference object. Now sometimes that reference object is a human being. That's why we kind of talk about anthropometry as a proportional tool, but it kind of leads us into the discussion about scale. So scale, often is something that we can't perceive unless we have a reference object. So for example, this is a building that Frank Gehry had done several years ago, and there's a sculpture of binoculars that is incorporated as an installation into that building. And unless you can start to see reference objects, like, if the woman were not standing in front of the binoculars, you might be able to look at the windows and start to figure out how big these binoculars are, but with her standing there, you can see exactly how big they are, because our mind perceives a person within a range of heights. Unless she's a 35-foot tall person, we're going to be able to tell visually and kind of let our mind know how big this is. And that's kind of how scale works. You're always searching mentally for something that is referential or something that makes sense to you so that you can tell how large or how small something is. One type of scale that we look at is visual scale. So again, as we're perceiving a building, as we're looking at it, this is Notre Dame Cathedral in Paris. If we didn't have all of the people at the very bottom of the photograph, and we didn't have the buildings on the two sides, then it would be more difficult to visually place the scale of the windows of this church. It would be difficult to place the scale of the doors even, because there are sculptures of saints running along the tops of the kind of bottom three arches, and those are not necessarily the size of actual people. So again, that's a little bit deceiving. And even the doors, if you didn't have actual people there, you might think those doors are like the size of a person, when in reality, instead of those being like 6'8" or 7-foot tall doors, they're probably 5 times that size. And the size of an actual person is about 1/5 of the total height of those central doors in that center archway. So visual scale gives you some reference pieces and reference points that allow you to understand visually and mentally and psychologically how big or small things are. Now, some buildings can have multiple scales operating simultaneously. So the towers, if those were isolated, in your mind you're thinking, how big are these, right? How large is this thing? And it's really in proportion to other elements of some known size. So then you'd start to maybe work your way down to the building, maybe start to look at the doors, but having the person or people there in relation to the doors is what really allows you to understand the building and understand how big it is. Now, human scale, visual scale can reference something that is either a human or non-human object, but human scale is what really lets you understand what that space might potentially be like to inhabit. And so when we're looking at the drawing on the left, this is what we'd refer to as kind of monumental scale. So that archway is much larger than a person, but you can't tell that until you see the people in the drawing. And if you didn't have that, then you might think that archway was like twice as tall as a person instead of 15 times as tall as a person. And so that human scale really helps you understand what the building is like in relation to a person. Now, the kind of section cut on the right is much more scaled to the size of an actual human. And so when we look at this, you can start to understand what it would be like sitting in that chair on the second floor and reading the newspaper with that lamp overhead. Or because you can see this man kind of walking into the first floor, you can understand what that would be like for the roof overhang to be just over your head by a couple of feet. So human scale definitely helps us understand what that space might be like in relation to humans. Now, of all the dimensions, when we're talking about rooms, of all the dimensions that affect human scale and human perception the most, it's typically the height, because if the height of a room is too low, then physically we feel like it's almost coming down on us. And if it's too high, then you might feel like the room is kind of overwhelming, or it's kind of has a silo effect, like it's too tall. But that vertical dimension of space typically affects people's perception of a room more than altering the other dimensions. So, for example, if we had a room and it was a certain length and width and height, if we increased the width by a foot, people wouldn't notice it as much as if you increased or decreased the height of the room by a foot, because it's that spatial perception that is most felt by humans when they're entering a space. Some other things that can affect the scale or the human scale of an area are the color of its surfaces, the patterning or texture of its surfaces, the shape of the openings within the surfaces. For example, if a wall, if there are 4 walls in a room and the height of the ceiling is very tall, if there are large openings, then it doesn't feel as confined because you feel like you've got space around you, or you could move into an adjacent space. Or if there are fixed elements within the space, that's going to affect how humans perceive the overall experience of the space. Scalar comparison just means that you're literally comparing the scale or shape or size of one building with another. And sometimes when we look at large buildings, these are tall buildings, then you might think, well, this building is fairly tall, but there's no human scale that's shown in this diagram. We're just looking at the comparison of tall buildings to tall buildings, and so because they're all quite grand in scale and quite monumental in terms of human scale, to put a person in any of these would be almost a little speck, right? Because they're comparably so small in comparison to these other buildings. But we're talking about comparing scale or scalar comparison. It just means that we are relating one object to another, one architectural building or architectural object to another, to see how it compares size-wise and also its features in relation to one another.